Great. Thank you very much, Professor Chen, for that kind introduction. It's really an honor to be here. And I would like to tell you today about some recent work related to artificial atoms and waveguide QED. And before I get started, I want to also acknowledge Franco Nori and his team from RIKEN, whose work this first part will be based on. And the second part is based on an idea from Yasu Nakamura's group back at RIKEN. And I'll point that out as we get to those two works. The title is Giant Artificial Atoms and Molecules and Chiral Photon Emission with Waveguide QED. So to get started, I'd like to introduce what we think of as a small atom. And actually, you could remove the word small, because when we think about atoms, we're usually thinking of them in this small regime. What we mean by that is if I'm driving a transition in an atom, the atom's spatial extent is small compared to the wavelength of light. So we would think it's a small atom compared to that wavelength. And this allows us to make an approximation called the dipole approximation as we calculate transitions and transition rates. So we associate a point-like object, an atom, with a dipole approximation. Most of what we work with is, in fact, in this limit. If we think of natural atoms, their radius is about an angstrom. The wavelength of light is 100 nanometers to a micron. And so if we look at this ratio, 10 to minus 3, 10 to minus 4, that's pretty small. You might think that by going to Rydberg atoms, where we excite an atom into a highly excited state, making the electron cloud very large, okay, maybe that's a large atom. But in fact, that also reduces the driving frequency, which increases its wavelength. And so if the radius of this is maybe 10 to 100 nanometers, the wavelength of the radiation in the microwaves is much, much smaller. So as a result, this ratio is still deep in the small atom regime. And then finally, superconducting circuits. Similarly, the superconducting circuits that I'll talk about are quite large, 100 microns. But again, we're driving them in the RF or the microwave regime. And so this ratio is still at the 1% to 10th of a percent level. So all of these are small, natural, and artificial atoms. But with superconducting qubits, they're electrical circuits. And we can make wires which connect that circuit to multiple places. And so as a result, we can go into a regime where we have effectively a giant atom that's coupling to the field at multiple points, and those points then will discretely couple, and therefore we need to consider quantum interference between those points, both emission and absorption. And this is enabled by the fact that a circuit, of course, can be wired and coupled to a drive line at points that are spatially separated. So we're going to take advantage of that in this work. What it means, though, is that the dipole approximation is no longer valid in this limit, and we just have to consider the self-interference along with the phases that are accrued between the emission and absorption points. So in this work, we're leveraging the size of our qubit, its connectivity, and quantum interference to realize high-fidelity operations in what's called a waveguide quantum electrodynamics, or QED environment. I'll explain what that means. So the outline is two topics. One is waveguide QED and giant artificial atoms. This is the work with Franco Nori and collaborators. I'd like to recognize Bharath and Dan, who did the work. And I'll talk about the second topic later. Superconducting qubits are sometimes called artificial atoms because they behave in some ways like atoms. And one example of a quantum circuit is an LC oscillator. We know that from electrical engineering. It has a resonance frequency 1 over square root of LC. And it is indeed an example of a harmonic oscillator. And if we look at the potential profile of a harmonic oscillator, it is quadratic. And if we cool this oscillator down to a low enough temperature, and we solve Schrodinger's equation, we can find that there are discrete energy levels, and we can label them by the number of excitations of our harmonic oscillator. Okay, so if we build an LC circuit at room temperature and cool it down at a cold enough temperature, okay, how cold? Well, the energy scale kT should be much less than h bar times the resonance frequency of the circuit. And if that's the case, then these levels are discrete and we can see them independently of one another. So this is a quantum circuit. However, it's not very useful for quantum computing. And the reason is that if we try to drive the 0 and 1, we also drive 1 to 2 and 2 to 3, et cetera, because these are all resonant transitions. They're degenerate. So we need to somehow break that degeneracy if we want to make a qubit. And the way that we do that is to use a Josephson junction. And Professor Chu introduced Josephson junctions this morning. But basically, we're talking about two superconducting leads separated by a thin insulating barrier. And we represent it by this symbol here, a cross. And there's a current flowing through it. There can also be a voltage across it. And Brian Josephson gave us these two relations for the current and for the voltage. And I'm not going to worry about that here, except for how we use them, which is that if we combine them in the usual way to define an inductance, we find that that inductance is highly nonlinear in the current that's flowing through the junction. So this is the definition of a nonlinear inductor. Now we can also look at the energy, the integral of current times voltage, integrated over time, and we find that this potential now looks like a cosine. So it's no longer harmonic, it is anharmonic, and the consequence is that if we replace this inductor with a Josephson junction that's nonlinear inductor, this is now an anharmonic oscillator. The cosine potential is shown here in blue, and the consequence is that these level transitions are no longer degenerate. They have a different frequency. Okay, that's good, because that means I can define 0 and 1 as my qubit and drive transitions between it without exciting the higher levels, right? So that's a unique difference. So there are many types of artificial atoms that are built from this concept. You might think of this one as our hydrogen atom. It's the simplest one. But by adding more junctions, more capacitors, more inductors, we can make many different elements in this Mendeleev table of artificial atoms. So the second term I want to introduce is waveguide QED, and to contrast that, we should first remember what cavity quantum electrodynamics is. And this is the dominant architecture that's used for superconducting processing today. So if you have an atom in free space, we remember that free space has basically a quasi-continuum of modes that would love to take the energy away from our qubit. And to protect a qubit or an atom from this quasi-continuum of modes in the environment, we can stick it inside a cavity. And now the cavity has discrete energy levels separated by the resonance frequency of the cavity. And if we place our atom's transition frequency off resonance with the cavity resonance, then effectively this atom is protected from the environment. And the rate that it decays or energy can leave is related to kappa now, which is basically the transmissivity of this mirror, the rate at which it decays. But inside, the atom can live a long time. It exchanges energy with the optical field at a rate g. And of course, energy escaping to this environment is not the only way that the qubit could lose energy. It could lose energy to internal degrees of freedom, and that's represented here by gamma. So this is how superconducting qubit architectures are basically driven today. Now, we can contrast that with waveguide quantum electrodynamics, where we couple qubits, one or several of them, to an open waveguide. But an open waveguide is a continuum of modes, again. And so this seems like a really bad idea because the qubit would lose its energy to the waveguide very quickly. But we want to do it because we remember that we would like to make interconnects between different qubits or even different chips, especially if we want to architect a larger scale quantum computer. And it's much better to do that along a waveguide because we can just send a photon from one place to another, whereas here the photon would bounce around the cavity many, 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 many times before it finally escapes. But then the question is, we're faced with two challenges. If we want to use this architecture, how can we avoid the always-on strong dissipation of this quasi-continuum of modes, which in electrical engineering terms we'll call the 50-ohm environment? And then second, even if we can do that, can we engineer interactions that are mediated by the waveguide, but also avoid the dissipation? Okay, and those are the two questions we want to answer. So, one thing we can imagine is that we know that if we put an atom in free space, this is an atom, we can drive it. And typically we'll think of driving an atom as with a plane wave. And when the plane wave hits this atom, it may excite it from the ground to the excited state. But when the atom emits, this is a scattering problem, and it will emit spherically. In fact, in 3 dimensions, it is a sphere. And what we see is that although there's a very beautiful interference pattern that arises, it's not